Hi. Um, so yeah, I am, I guess, a cryptographer by training. I'm definitely a computer scientist. But I guess I have an undergraduate degree in political science, and I work with a statistician. And my work is really motivated by trying to sort of imagine someone in that kind of setting, right? You know, an economist trying to do research with data and trying to provide tools that I think would be useful for them to actually carry it out. And yeah, so the sort of main official paper that I'm presenting on here is work with Simon Couch, Zeki Kazan, Kaiyan Shi, and Andrew Bray, but there's work from a bunch of other people here that's going to get talked about. Yeah, including some current undergraduates who might be looking for graduate school opportunities if you're interested. Okay. So here's the setting I'm going to focus on. Say you want to know something like, do people with different blood types also have different blood pressure? Right? And you get data that looks something like this, right? Lots of individuals, you know their blood type, you know their blood pressure. And then you want to analyze it, right? So the obvious thing to do is like compute the average blood pressure in each group, right? And then the question is sort of, is that a real difference, or is that just plausibly random sampling variation, right? And you answer this with a hypothesis test, right? For this particular setting, you would do ANOVA, analysis of variance, generally. You assume that the blood pressures are normally distributed within groups, and you calculate a test statistic. So in this case, your test statistic is the F statistic. It's this function of the database, and the details are not important, just for the sake of defining it. N is the number of people, and K is the number of groups. Then you have these messy formulas for the numerator and denominator, and J is the number of things in a group. Yj bar is the mean of the jth group, and so forth. But you know, there's a formula. You calculate a test statistic. Then you have your null hypothesis, right, which is that blood pressure is the same in each group, and you calculate a p-value. Right? The probability that your test statistic would have been above the thing you found on the real data if you were drawing your data according to the null hypothesis. Right? This is all quite standard, and you've generally set some alpha value ahead of time, usually 0.05 or something close to it. And if the p-value is less than that, you reject the null hypothesis. Right? You say that this is sort of implausible as random sampling variation, right? This is a very standard kind of analysis. If you look at, you know, research papers in political science or medicine or economics, right, it's lots and lots of this, and a lot of focus on whether p came out to be less than alpha or not. So say you want to do that privately, right? How can you do it? So first idea we had, right, and I should say, sort of before we looked at this problem, no one had attempted to privatize this. The first idea is just add Laplace noise to your test statistic, right? That's the thing that gets you as close as possible to the test statistic. The problem is F has unbounded sensitivity, right? There's a worst case where the denominator is basically 0 and the smallest change can cause arbitrarily large effects. Okay, so what we did instead was we added noise to the numerator and the denominator separately. Those both have some sort of nice quantifiable sensitivity, and you can just add noise there. Right, the top turns out to have sensitivity 9 plus 5 over n, and the bottom has sensitivity 7, and you know. But there's other problems. Adding noise separately to the numerator and denominator creates a complete mess of a distribution. There's really like nothing nice you can say about it at that point. But you need to know the reference distribution to compute a p-value, right? The test statistic doesn't do anything on its own, right? You need to know to what to compare it to. So we simulate the reference distribution, right? We can't figure it out analytically, fine, you simulate. But when you privatize it, you lose this nice property that the F statistic previously had, at least when you privatize it like this. The null hypothesis that you're comparing to is not a single distribution, right? There are lots of distributions that have the property that the mean is the same in all the groups, right? The means differ, and particularly the variances differ, right? There's different distributions that are consistent with this. And the F statistic is what we call scale free, and you get the same distribution regardless of those standard deviations, and therefore you can sort of compare and not worry about it. This isn't scale free anymore. But we're lucky, you don't have to release the F statistic. If you're doing it by adding noise to the numerator and denominator and then dividing them, you can just release them, and the rest is post-processing. And the denominator turns out to also give you a really good estimate of the variance, just conveniently. And it turns out that it's good enough that you can use that for simulating your reference distribution, and you get p-values that are valid. You can sort of check that you're not accidentally rejecting things too often. And this gives us a private ANOVA test. And we can measure the power, right? So the power of a hypothesis test is for a given effect size, right? In this case, 3 equal groups that differ by 1 standard deviation each in their means, right? We can say sort of how much data does it take to actually notice that that's not something from the null hypothesis, right? How often will you reject given a certain amount of data from that distribution? Get this line, right? Takes to get 80% power, right, to sort of start noticing most of the time, it takes about 4,250 data points. But the public statistic, right, if you don't care about privacy, it takes 19 data points. And that's a large loss. You know, and this is at epsilon equals 1. Right, you might want to go lower than that, right? Yeah. So, I mean, now we have a private test, but it's not, right? The cost of doing something privately instead of publicly is large. So how can we improve that? And I should say this is work with Ira and Marika, who are here. But the initial idea for how to improve it is just add less noise, right? Just get a more accurate value. And we thought about, you know, is there a way to make our proof tighter and get a better sensitivity bound? But surprisingly, we tried just running it as if the sensitivity was a third of what it actually is or something like that, and it turned out not to help very much. You don't gain a whole lot in this setting just by turning the noise down a bit. So what we did instead was change the test statistic. So this is the test statistic that we had before, and this is the new one. And the thing to notice here is that all we did was we changed the squaring to absolute value. Right. So these are all measures of distance between things, and we're just using absolute distance instead of squared distance to measure that. Conceptually, this is perfectly nice. This is just as nice as squared distance, right? I mean, you can sort of argue as to which seems more natural to use. The absolute values do lose some nice mathematical properties, though. But I mean, that's fine, right? And it has lower sensitivity, right? 3 for the denominator and 4 for the numerator. But more importantly, the values that you're adding noise to under the sorts of databases where you might be detecting some sort of result are just a lot higher to begin with, right? And it's not the amount of noise you add, it's the noise to signal ratio, and this just makes it much better. And we go from 4,000 plus data points down to about 280, which is a big change. But then we had another idea. So I had another set of students who were going to work on KRUSKAL-WALLIS testing. KRUSKAL-WALLIS is an alternative to ANOVA. It's another test you can use in the same setting. The advantage is that it does not assume that the data is normally distributed. Right? That's sort of the classical reason why statisticians would use this test. The disadvantage is that as a result, you get lower power. Now, I should say it's talked about everywhere as having lower power than ANOVA, but when we actually did simulations and tried to notice that effect, it is at least small enough as to be not clearly detectable as anything other than Monte Carlo noise in our simulations. So it turns out this is not actually that much lower power in practice. But anywhere you read about it, it will say that it is. The way KRUSKAL-WALLIS works is that it uses ranks instead of raw values. Right? So you take your blood pressure and you order it. And then, well, actually, wait. So one thing I should say about ranks is anytime you're working with numbers with differential privacy, you usually have to put some sort of artificial minimum and maximum value on it so as to keep them in some range, right? You don't have to put that value, that bound on the actual data, but your sort of first analysis step has to be clip everything to that range and then proceed with whatever else you're doing so that you can limit the sensitivity. Ranks don't have that concern, right? Anything that's using ranks within your data, there's a minimum and maximum rank, and it's always sort of straightforward. Okay, so the way the test statistic works is, well, you do this. This is just another random messy formula, where Rij is the rank of the ith element in the jth group. Ri bar is the average rank within group I. You get this test statistic. And having seen how well the thing worked before, I figured, okay, let's change everything to absolute values. Fine, right? That's a test statistic. It turns out it has sensitivity 8. There's nothing deep about the sensitivity analysis. It's a couple cases you have to go through. Now, other things get tricky. In the non-private version, there's a certain distribution you can compare to. Once you privatize, the reference distribution now depends on how the sizes of groups are distributed, right? Are your n data points in groups of equal sizes or lopsided or something? And what we do is we just use the reference distribution, assuming that the groups are of equal size. This is conservative, we think. What we're able to prove is that this maximizes the expected value, right? What you want to do is use a reference distribution that's, if anything, too high, so that you have your validity and you don't reject by accident. So we can prove it maximizes the expected value. What we actually want to prove is that it maximizes the value at every quantile. We can't do that, but experimentally it's true. We ran a bunch of simulations. It seems to work fine. And then we can do a power analysis again. So this one is the green line. This gets us down from 280 to 63 data points needed for this particular effect. And I should say we tried this with a bunch of different effects with a lot of epsilon values. Obviously, how much data you need depends on all of these things, but the general ordering and effect sizes here are roughly consistent. So that cuts the cost of privacy by another, 70% or something. And I'll say this is really recent, and we haven't checked everything yet. But I think there's work coming soon from the people I'm working with this summer gives a new test for this that gets it down to about 37 data points. Which I should say, we're not trying to, we came up with a technique for something else, and then we tried applying to this, and it turned out to work really well. I didn't think you could get much better than this, but it seems that there was still room for improvement. Maybe there is more, right? But when you're talking about how practical it is to use differential privacy with someone who has to collect data in a way that is, you know, energy or money intensive, or where it's hard to find enough data, right? How much more data do you need is the way that people sort of think of this cost. And getting this closer and closer to what you could do if you didn't care about privacy, I think is important.
Sorry, one question. Is this KRUSKAL-WALLIS based as well, or is this something totally different?
It's KRUSKAL-WALLIS with some other stuff added on top. I'm happy to talk about it offline if you want. Yeah. So then I'll talk about some other stuff a little bit. There's the two-group case, right? In the public setting, there's a special test you can do when there are exactly two groups that works better. It's called Mann-Whitney. It has higher power than KRUSKAL-WALLIS. When we try to privatize it, the sensitivity depends on the group sizes in a really inconvenient way. And we did our best, but at least the way we could do it, KRUSKAL-WALLIS actually seems better. If you don't have any information on the side, like exactly how many people are in each group, KRUSKAL-WALLIS seems better, which is sort of different than what's the case in the public setting. And I think sort of one general theme I have here is that sort of like lots of things just work out differently in the private setting than they do in the public setting. And the downside, or I guess upside, if you're looking for research problems, is that we can essentially redo all of statistics under differential privacy, right? Which seems crazy, but also is to some extent what we need to do, right? Okay. Yeah, so then I think another maybe illustrative example is from the same paper, is if you look at paired data, right? So this is two groups, but the two groups have some sort of correspondence between them. Maybe these are before and after measurements of some sort of treatment, or husband and wife, or whatever it is. Right, so in this case, there's the WILCOXON signed rank test. This is the standard public non-parametric thing. This was the only non-parametric test that was privatized prior to our work. This was done by Task at Clifton. And the idea here is you take your data, you compute a difference, right? You subtract one from the other, and then you rank the data, right? So you drop the zeros, and then you just say, okay, right, this third row is the lowest change, so that's rank 1, and then the fifth row is the next highest change, and so forth. And you list the ranks with a sign equal to whether they, indicating whether they increased or decreased. And then you just add up those signed ranks, and that's your test statistic. This is what people do in the public setting. Task and Clifton privatized this. But they ran into some problems, right? So one problem is that the reference distribution depends on NR, which is the number of non-zero change rows, right? So you drop all these zeros at the beginning. Your reference distribution depends on how many zeros you dropped. So they have two options. One is their high utility option, where you assume that at least 30% of the rows are not zero, which seems reasonable and realistic data, but it's not actually differentially private, so it raises all sorts of questions about composition and other things. My guess is it's fine, but like there's a lot of work to do there. They also have a high privacy version where you add k rows with change infinity and k with change negative infinity, and then you know there are at least 2 k rows that have some change in them, and you use that. What we do instead is use something called the Pratt variant of the WILCOXON, which we spent a lot of effort recreating before we found out that it was published in like the 1930s or something. And it's basically sort of what seems to me like the more obvious thing to do, which is just rank all of them and consider things with zero change to have sign 0, right? So here these count as zeros, but like the lowest change one is now the third one because the zeros have less change than that. And then you just use the sum of those signed ranks. It turns out in the public setting, this is basically equivalent to the other thing, and no one cares about the difference. And for whatever random historical reason, the other thing became the standard, and this got forgotten by everyone. But you know, it's not meaningfully different, except that it turns out to privatize massively better. You can just add noise to this and everything. Then there's another problem, which is that the reference distribution now has no closed form solution because you added Laplace to something and it makes everything awful. So in the prior work, they proved an upper bound on the critical value theoretically. And we just used Monte Carlo simulation to estimate it. And this turns out to make quite a difference. So here are some critical values, right? The test statistic at which you would reject. And you know, especially with low epsilon, ours are still wildly higher than in the public setting, but they're a lot closer. And this is what you get. So the pink line there is our private WILCOXON, and the 2 lines on the right are the 2 prior tests. We got sort of most of the way to the public test. Now, what we wanted to do was see how this compared to the parametric test, right? What we found with the ANOVA setting was that surprisingly, the non-parametric thing, which is supposed to be sort of lower power in the general public setting, privatized better and became the more powerful test in the private setting. We wanted to see if that was true here. The parametric equivalent to the WILCOXON is a t-test. This is a candidate for the most used hypothesis test out there. I learned it in 10th grade AP statistics. And there was almost no work on this at all before us. There are a couple things. Salia gave a test, but it's not valid. It rejects at rates above alpha for significant parameter space. Gabardi, Rogers, and Chaffet simultaneous to us did something in the local DP setting, which obviously is much more restrictive. And Karwa and Vadan had confidence intervals, which are essentially isomorphic to a t-test. But those have great asymptotics, not good low end performance, which is what we're looking at. And that was basically it. And I think it says something not great about our research community that in 2019 or whenever we were doing this, no one had published a practical t-test you could run on data, right? This is sort of one of the most basic things anyone would want to do with the data set, and no one had said how to do this with differential privacy. So we gave a t-test just for the sake of comparison. We made one up. We designed it, it works basically the same way the ANOVA tests do, and it turns out ours is better. The WILCOXON is better than it. Right, the ranks thing works really well. So that's sort of the main technical stuff I want to say, but I thought this is maybe a good setting for some maybe broader lessons that you got out of this. So one, the least broad lesson is ranks work really well. There's probably other stuff you could do with ranks that's really powerful. When you're doing this kind of research, I think it's really important to focus on the end goal, what you're actually trying to learn. So you're trying to compute a p-value or an accept or reject decision, right? Not an estimate of the test statistic. The test statistic is the thing that you compute on the way to the thing you actually care about. And if we sort of get distracted and try to come up with the most accurate estimation possible of this particular test statistic, right, we're maybe not achieving the goal we really care about. Another thing I would say is that we shouldn't hold private statistics to a higher standard than statistics. So for example, we just Monte Carlo'd the reference distribution for the WILCOXON, where prior work proved an upper bound. I've seen a lot of stuff where computer scientists try to prove something that statisticians just experimentally confirm and move on from. And yeah, I think there are times when we sort of expect a level of rigor out of private statistics that isn't there in the public statistics that we're trying to estimate, and it makes it worse. I think you can often get more out of innovation on the statistics side of things than on the privacy side of things, right? Everything we did was just add Laplace noise based on sensitivity, right? That was the privatization mechanism for everything. And we had reviewers who told us there's nothing interesting here because it's just the Laplace mechanism, right? I think you have to be very familiar with the privacy, but then focus on the other thing you're trying to achieve. I would also really make an argument that we should look at concrete analysis of small n more often. Asymptotics are great. I love reading those papers, but we shouldn't always be doing asymptotics. Right, and I guess the argument I would make here, I think computer scientists pick up asymptotic analysis sort of by habit because it's what we do with algorithms, right? But with algorithms, the hard case is the large n case, right? Everything works if your input size is tiny. So we care about what happens as it gets large. But everything works if your database is large enough for differential privacy, right? The problem is having smaller amounts of data. So I think that the sort of traditional argument for asymptotic analysis doesn't apply here as well. Interdisciplinary collaboration is important, right? Not necessarily so much for the knowledge, but not for the knowledge of specific technical material, but for knowing things like, yeah, no, you can just simulate that, it's fine, right? And in general, there's a lot more to do. At one point, I tried to have a student sort of like pick a paper, right? An economics paper, a political science paper, something like that. Something that had a publicly available data set. And just for the sake of trying it out, try to carry out the same analysis with differential privacy as a constraint. And it very quickly became clear there were not any papers we could find where it was remotely possible. And it's because when you try to actually do a full analysis, there's all sorts of little things that there's no differentially private mechanism for, right? That people haven't looked at before. So unless you have a PhD in differential privacy and you're going to develop lots of new stuff, we just don't yet have the set of tools for that out there, and I wish we did. I think we should think about whether we make people interact by query or by privatized microdata or summary statistics or what. And I mean, I think we can get better accuracy with the query model. But I think we need to think about how we make that practical so that we don't get these other concerns that sort of make people write that off from the beginning as not a way we can release data. And in general, I think there are just other things that might come up as a result of differential privacy that we're not really thinking about yet. So for example, this is a randomized hypothesis test. If you run it multiple times, you might get different answers. Right? In theory, that's fine. Nothing about why a hypothesis test is good or means the right thing breaks down if you randomize it. But in practice, right, where we already have problems with people just running analyses over and over again until something turns out to be significant, the fact that you could run the same analysis over and over again and eventually it will turn out significant is a problem. And I think there are going to be other practical problems like that as we move into things being used more in practice. I think it would be good to think about those proactively as much as we can. So yeah, I'll leave it there. Thanks.